So, um, on June 4th, 1996, the European Space Agency launched the Ariane 5 rocket.
Right, which was just this massive, uncrewed space launch vehicle.
Yeah, exactly.
Yeah.
And it was carrying, roughly $370 million worth of scientific satellites.
A staggering amount of money.
Just a completely staggering payload. It was the culmination of, a decade of engineering, and exactly 39 seconds after liftoff, the rocket violently, just abruptly veered off its flight path.
And that's when the aerodynamic forces literally ripped the boosters from the main stage.
Yeah, the entire vehicle just self-destructed. It turned into a massive fireball over French Guiana.
It's honestly one of the most infamous moments in aerospace history. And the truly fascinating part is what actually caused it.
Right, because it wasn't a faulty thruster. It wasn't like a structural integrity issue with titanium shell or anything.
No, the fuel was fine. The hardware was essentially perfect.
Exactly. The culprit was a single tiny piece of software.
Specifically, it was a data conversion error. Like, a piece of code was trying to stuff a 64-bit floating point number, which represented the rocket's horizontal velocity, into a 16-bit integer space.
Which is, what, the digital equivalent of trying to pour a gallon of water into a shot glass?
That is exactly what it is. The system just couldn't handle the overflow, so it threw an exception, and then the primary guidance computer crashed.
And the backup crashed too, right?
Yep. The backup computer crashed for the exact same reason, because it was running the same software, so the rocket suddenly thought it was completely off course.
Wow. 39 seconds and nearly $500 million vaporized because of a software glitch.
It really puts it in perspective.
It does. And we are opening with that story today because we need to fundamentally shift how you, the learner, think about computing.
Absolutely, because you're gearing up for a major university exam.
Yeah, a comprehensive multiple-choice gauntlet, and it's designed to test your mastery of the absolute fundamentals of computer software.
And look, you've probably got a towering stack of textbooks and study materials. But if you just try to memorize the bolded terms, flashcard style, you are going to fall right into the traps the test makers have laid out.
Oh, 100%. Rote memorization is just too brittle for this level.
It really is. On an advanced university exam, the distractors, the incorrect multiple choice options, they aren't going to be obvious throwaways.
Right, they'll sound completely plausible.
Exactly. They're going to be plausible descriptions of adjacent technologies. So if you don't understand the underlying mechanics, the actual why and how of the architecture, you're just going to be guessing.
Which is exactly why we're here today. Our mission for this deep dive is to distill that massive syllabus into basically the ultimate audio study guide.
The overarching architectural map, so to speak.
Exactly. We are focusing with absolute laser precision on 5 critical software categories today. We're looking at system software, application software, embedded software, proprietary software, and open source software.
But, and this is key, we aren't just going to read dictionary definitions to you.
No way. We are going to rip open the casing and look at how the gears actually mesh together.
To do that, we have to start with a baseline philosophy that your source texts establish right out of the gate.
Okay, let's hear.
There is a rigid dichotomy between hardware and software. So hardware is the silicon, the copper wire, the motherboard, all those physical transistors.
The stuff you can actually kick if you get mad at it.
Right, exactly.
Yeah.
But on its own, hardware is just dead material. I mean, it's a very expensive space heater.
Yeah.
It can pump electricity, sure, but it possesses absolutely no logic.
So the software is the animating force. It's that intangible logic, the complex set of instructions and procedures that dictate exactly how those electrical impulses should be routed to actually accomplish a task.
That's a great way to put it. The hardware is the muscle, but the software is the nervous system and the conscious mind combined.
And I like to use an analogy here to set the tone for the rest of the deep dive. Think of a computer as a massive, high-tech office building.
Okay, I like this.
Right. So today, we're going to explore who actually manages the building, who does the specific jobs inside the offices, who the invisible workers in the basement are, and ultimately, who holds the legal blueprints to the whole structure.
That maps perfectly to the 5 categories, and that nervous system, or that building structure, is highly layered. It's strictly hierarchical.
So it's not just a free-for-all in there.
Not at all.
Okay.
The computer doesn't just have one massive block of software doing everything all at once. It has distinct levels of privilege and responsibility.
Yeah.
And the deepest, most fundamental level, the autonomic nervous system of the machine, is what we call system software.
Which is our first category, pillar number 1 for your exam. So let's pull the definition directly from your syllabus.
Go for it.
The textbook states that system software is a collection of programs directly responsible for controlling, integrating, and managing the individual hardware components of a computer system.
Right.
It is the interface between the user, the applications, and the raw hardware.
So going back to your office building analogy.
Yeah, system software is the building management. It keeps the lights on, it keeps the elevators running, and it ensures that the office workers, which would be our application software, have a safe, stable environment to actually work in.
Exactly. And if we really want to understand the nuts and bolts here, we need to look at what's actually happening when you press the power button on your machine.
Because system software isn't just one single program, right?
No, it's a whole suite of low-level tools. But the absolute core of it, the undisputed dictator of the entire machine, is the operating system, or the OS.
And your sources are super clear on this for the exam. A computer cannot even boot up without an operating system.
It's completely impossible.
But I want to get past that basic dictionary definition. What is the OS actually doing under the hood? Your text lists 5 major functions, and I know these are just prime targets for those tricky scenario-based exam questions.
Oh, absolutely. They love testing on these. So let's break them down. The first major OS function is process management.
Okay, process management. Let's define what a process actually is first.
Simply put, a process is a program in execution.
Right, because when an application is just sitting on your hard drive, it's just a file, isn't it?
Exactly. It's just dormant code. But the second you double-click it, the OS loads its code into the active memory, and boom, it becomes an active running process.
Got it. Now, historically, early processors, the CPUs, they could only execute one single instruction at a time, right?
Yeah, exactly one.
So if you have like 50 processes running on your laptop right now, your web browser, a music player, 50 background system tasks, how does a single core CPU actually handle all of that simultaneously?
Well, it has to juggle constantly.
And how it juggles, that's what we call scheduling, right?
You nailed it. The OS has a specific component called the scheduler, and it determines exactly which process gets access to the CPU and for exactly how many milliseconds.
Now, your texts highlight a really critical evolutionary step in this juggling act. You need to know the difference between cooperative multitasking and preemptive multitasking.
This is a huge exam topic.
Let's unpack the mechanics of it, because cooperative multitasking just sounds almost, I don't know, naive, like the OS is just crossing its fingers and hoping the software plays nice.
Honestly, it kind of was naive, and it was an absolute nightmare for stability.
How so?
Well, in cooperative multitasking, which was the standard in early versions of Windows and classic Mac OS, the operating system would hand control of the CPU over to a running process, say a word processor, and then the OS basically had to just sit back and wait for that word processor to voluntarily say, okay, I'm done with my calculations for this millisecond, here's the CPU back.
Oh, wow. So if a program had a bug or just like got stuck in an infinite loop while trying to format a massive document,
it would never yield control back to the OS. Ever.
And the entire system would just freeze up.
Exactly. The OS had absolutely no mechanism to rip the CPU away from the malfunctioning program. You just have to physically reach out and hard reboot the machine.
That is a massive architectural flaw. And I assume that's what necessitated the shift to preemptive multitasking.
It is exactly why we shifted.
Okay, so how does preemptive multitasking change the actual physics of the system? Like, if I'm the OS now, how am I preempting a stubborn program?
By using what's called a hardware interrupt.
Okay, a hardware interrupt.
Yeah. In a preemptive architecture, the OS is the absolute, unquestioned master of the domain. It relies on a physical hardware timer that's actually built into the motherboard.
So it's not just software asking software nicely anymore.
No, not at all. The OS says to a process, you have exactly 10 milliseconds of CPU time. The process starts calculating its math, but when that physical quartz timer ticks down to 0,
Time's up.
any time is up. The hardware sends an interrupt signal. It literally pauses the CPU, stops the application mid-calculation, and violently hands control directly back to the OS scheduler.
And the OS just takes over.
Mm-hmm.
Then what? Does it save where the program was at?
Yes, the OS saves the exact state of that paused program, which, by the way, is a term you need to know for the exam. a context switch.
The context switch. Okay, write that down, learners.
The OS takes the current contents of the CPU registers, saves them safely to memory, loads the state of the next process in line, and lets that one run.
And it's doing this, what, thousands of times a second?
Exactly. That is exactly why you can watch a high-def video and download a massive file simultaneously without the video stuttering. The OS is ruthlessly slicing up the CPU time and preempting programs before they can hog the system.
That is a phenomenal explanation to keep in mind for the exam. Because if a multiple-choice question describes a scenario where an OS is forcefully reclaiming CPU time using a timer, you instantly know it's preemptive multitasking.
And that falls squarely under process management.
Correct. Awesome. Let's move to the second major OS function, memory management. And by memory, in this context, we are specifically talking about RAM, right? Random access memory.
Yes, RAM,
Right.
the primary workspace of the computer, the short-term memory.
So the textbook states that the OS coordinates this space, it allocates memory to processes, and it ensures they don't overwrite each other. But how does it actually do that?
That's the real question.
Because if I have, say, 8 gigabytes of RAM in my laptop, and I open an application, how does the application know exactly which physical memory cell to put its data in without hitting another program?
This is where we get into a brilliant concept called virtual memory and paging.
Okay, virtual memory.
See, when a human programmer writes an application, they have no idea what kind of computer it will eventually run on.
Right, they don't know my specific setup.
Exactly. They don't know if your physical RAM chip will be mostly empty or if it will be totally fragmented by 50 other running programs. So the OS essentially plays a massive magic trick on the application.
A magic trick.
Yes. The OS gives every single process its own pristine, continuous block of fake memory. That's the virtual memory.
Wait, so the OS just lies to the application. It says, hey, you have all this empty space, even if it doesn't.
It absolutely lies to it. The application boots up and thinks it has all the space in the world, starting cleanly from address 0. But under the hood, the OS memory manager takes that fake virtual memory and chops it up into standard size blocks, which we call pages.
Okay, pages. And then what does it do with them?
It scatters those pages wherever it can actually find empty physical space on the real RAM chips.
So it's completely fragmented in reality, but the application thinks it's all in one neat row.
Exactly. The OS maintains a massive complex ledger called a page table to keep track of it all.
So when the application tries to write data to its fake virtual address,
The hardware looks at the page table, translates that fake virtual address into the real physical location in the RAM, and writes the data there seamlessly.
oh, that makes so much sense. And this explains why programs don't constantly crash into each other.
Right, because if process A tries to write data into the memory space that actually belongs to process B, what happens?
I'm guessing the OS steps in.
Immediately. The OS memory manager detects that the virtual address doesn't correctly map to a physical page assigned to process A. It flags it as an illegal operation.
Oh, and in Unix-based systems, this is called a segmentation fault, right?
Yes, segfault. The OS instantly kills the offending process to protect the rest of the system from corruption.
Wow. So when my program unexpectedly quits out of nowhere and gives me a random segfault error window, I'm actually witnessing the OS memory manager actively assassinating a program to save the machine.
You are. The OS is acting like an incredibly aggressive bouncer protecting the VIP section of the RAM.
That is incredibly vivid. I love that. Okay, so that's process and memory. Let's look at the third core OS function, file management.
Right, moving from RAM to long-term storage.
Exactly. The OS organizes data on storage devices like your hard drives and solid-state drives. And the syllabus specifically highlights certain file systems you need to know, primarily FAT and NTFS.
Right. So FAT stands for File Allocation Table, and NTFS is the new technology file system.
Okay, why do we need these?
To understand why the OS needs a file system, you have to realize that a physical hard drive is just this massive expanse of billions of magnetic sectors or memory cells.
Just a huge blank desert of storage.
Exactly. If you save a high-res photo, the physical zeros and ones making up that image might be scattered across thousands of non-contiguous random sectors all over the disk.
So if I want to double-click and open that photo later, the OS needs a treasure map to find all the scattered pieces and reassemble them.
That map is the file system. The FAT system, which is older and much simpler, literally uses a simple table at the very beginning of the drive.
Just an index.
Right. It looks at the file name, and the table points to the very first sector where the data starts. At the end of that first sector, there's a little pointer that tells the OS where the next sector is, kind of like a digital scavenger hunt.
Oh, that's wild. It just jumps from clue to clue until the file is fully read.
Exactly. But FAT has major limitations, which is why it's mostly obsolete for main drives now.
Yeah, I know it struggles with very large file sizes, and it really lacks security features.
It does, which is exactly why modern Windows operating systems use NTFS. NTFS doesn't just use a simple lookup table. It uses a highly complex relational database called the master file table.
Oh, wow.
But more importantly for your exam, NTFS utilizes a vital concept called journaling.
Okay, journaling. What does journaling actually do in practice?
Well, imagine you are saving a massive 10 GB video file to your hard drive, and halfway through the transfer, the power goes out in your house.
Oh, that's the worst. Total panic.
Right. In the old FAT system, that data would just be half written, the sector pointers would be completely corrupted, and the file system itself might actually break. You'd have to run hours of disk scanning tools just to fix the drive.
But NTFS handles that better.
Much better. NTFS writes down its intentions in a secure log, a journal, before it actually moves any of the real data.
Wait, so it's like a to-do list?
Exactly. It says, I'm about to move these specific blocks. So if the power cuts out mid-transfer, when the system eventually reboots, the OS just looks at the journal.
And it sees the task was never finished.
It sees that a transfer was interrupted, and it cleanly rolls back all the half-finished changes, so the file system remains perfectly intact. No corruption.
That is brilliant. The OS is just constantly covering its own tracks to prevent data corruption. So that's file management. Next up on the syllabus is device management.
Another critical function.
We all know the computer has peripherals, right? Mice, keyboards, graphics cards, printers. The OS has to manage them. But the text specifically emphasized device drivers. I want to dig into the abstraction layer here.
Abstraction really is the key word for the exam. An operating system is a massive generalist. The engineers at Microsoft or Apple who create Windows or Mac OS, they have absolutely no idea what specific brand of printer with what specific physical ink nozzles you are going to plug into your machine 5 years from now.
That makes sense. So when I hit print in my Word document, the OS knows how to initiate a generic high-level print job. But it doesn't actually speak the native specific language of my obscure Canon photo printer.
Right. It doesn't know which physical hardware registers to trigger to move that specific print head back and forth. This is where the device driver comes in.
Okay, define the device driver for the learner.
A driver is a highly specialized, low-level piece of system software that is actually provided by the hardware manufacturer, not the OS maker. It acts as a translation matrix.
A translator.
Exactly. The OS sends a high-level generic command like print this image. The device driver intercepts that generic command, translates it into the exact proprietary electrical signals required by that specific printer, and then sends it through the USB port.
It's a literal interpreter. So if the OS doesn't have the right driver installed, it's just, shouting English at a machine that only understands binary Mandarin.
That's a perfect way to visualize it. And without that translator, the hardware is functionally invisible and useless to the OS.
Excellent. The final core function of the OS mentioned in your materials is security management.
A huge one in today's world.
The text described this as protecting against unauthorized access, managing user accounts, and passwords. But architecturally, at the nuts and bolts level, how does the OS actually enforce this?
It enforces it right at the hardware level using what computer scientists call privilege rings, or more simply for your exam, kernel space versus user space.
Kernel space. Okay, let's unpack that.
The very core of the OS, which is the kernel, runs in a highly privileged hardware mode. It has direct, unfettered access to the RAM, the CPU, and all the physical hardware.
The ultimate VIP access.
Exactly. Everything else, including the applications you run, operates in user mode, which is highly restricted.
So if a malicious program or, even just a poorly coded, buggy application tries to directly access my hard drive to delete a critical system file, it can't just reach out and do it.
No, absolutely not. An application running in user mode cannot physically touch the hardware. It must politely ask the kernel to do it on its behalf.
And how does it ask?
By using something called a system call, or a syscall.
Okay, syscall.
The application sends a syscall, the kernel intercepts it, and then checks the security management protocols. It checks your specific user account permissions.
So I'm logged in as a guest user.
Right. If you're a guest and you don't have the administrative rights to delete that system file, the kernel just flat out rejects the syscall and blocks the action. The OS is acting as an impenetrable membrane between the unprivileged applications and the raw hardware.
Okay, that perfectly covers the 5 functions of the operating system: process, memory, file, device, and security. But system software is actually a broader category than just the OS, right?
It is. The syllabus also includes system utilities.
The maintenance crew of the office building.
Yeah.
They don't write the actual business documents for you. They just perform specialized tasks to keep the system optimized.
Exactly. And let's look at the specific utilities your exam is likely to test you on. Disk compression is a classic example from the syllabus. The text specifically mentions older tools like disk doubler.
So how does compression actually work at a system level without, losing all my data? Because I understand that compressing a JPEG photo makes it blurrier and degrades the quality, but you can't make an Excel spreadsheet blurrier.
Right, a spreadsheet has to be exact.
Exactly. So how does it shrink?
You're touching on the critical difference between lossy and lossless compression. System utilities use lossless compression algorithms like Huffman coding.
Huffman coding, how does that work?
Well, imagine you have a text file that has the word "the" written 1,000 times.
Okay.
Instead of storing the full binary code for THE 1,000 times over, the utility algorithm replaces every instance with a tiny single symbolic placeholder, and then it creates a dictionary entry that simply says placeholder equals THE.
Oh, wow. So it mathematically reduces the redundancy of the data?
Yes, it shrinks the file footprint on the physical disk significantly, and then it instantly decompresses it by reversing the dictionary when you want to open it. No data is lost.
That's incredibly efficient.
Yeah.
Other utilities mentioned in the text are disk cleanup, which I think we all know. It scans for orphaned registry entries and temporary internet cache files, and it deletes them to free up physical sectors on the hard drive.
Yep, basic housekeeping.
And then, crucially, antivirus software.
Yes, antivirus is a huge one. Your texts use examples like Kaspersky, AVG, McAfee, and it is classified as a system utility because it actively patrols the low-level memory space and the file system.
Now, early antivirus mostly relied on signature-based detection, didn't it?
It did. It basically had a massive dictionary list of known viral code snippets, and it would just scan your files looking for a direct match.
But modern viruses change their code constantly to hide, right, the polymorphic viruses.
Exactly, they mutate. Which is why modern antivirus utilities have to use something called heuristic analysis.
Heuristic analysis. Break that down for us.
It means they don't just look for known bad code, they monitor the actual behavior of running processes.
So it watches what the program is doing, not just what it looks like.
Precisely. If a completely unknown program suddenly tries to open 1,000 system files and encrypt them in rapid succession.
That's obviously a ransomware attack.
Exactly. The heuristic engine recognizes that malicious behavior and violently kills the process, even if that specific virus's code signature isn't in any known database yet.
Fascinating. Okay, now, there is one utility listed in the text that always trips students up on the exam. Text editors, and specifically Notepad.
Oh, this is a classic trap question.
Right. Why is Notepad classified as a system utility instead of an application software like Microsoft Word? I mean, they both edit text. What's the difference?
It's all about intent and capability. Think about it. Microsoft Word is an application designed to format text for human consumption. It handles complex page layouts, proprietary fonts, embedded graphics, margins.
Heavy.
Very heavy. Notepad is a bare-bones utility tool that strips absolutely all of that away. It is designed to interact with pure, raw, ASCII, or hexadecimal text.
So who is actually using it?
System administrators, programmers. They use text editors to open raw configuration files, modify command line scripts, or read system error logs. It's a tool for editing the system's underlying code, not for writing a best-selling novel.
Ah, okay. The rich formatting in Word is actually a massive liability if you're trying to write a command line script. You just want the raw characters. That makes perfect sense.
Exactly.
Let's solidify all this with the industry OS examples from the text that the learners need to memorize. MS-DOS, which is the old command line OS. The Windows family like XP, 7.8, Vista. Unix, which is known for being a highly stable multi-user OS. And of course, Mac OS.
Right. And having laid this dense foundation, we need to immediately pivot to how the exam will actually test you on it. The multiple choice questions won't just ask for simple definitions, they will test your ability to differentiate these mechanical concepts in real time.
Okay, learner, pay attention. Here is your first practice question, ripped straight from the concepts in the source material. Listen closely to the distractors. A collection of various programs that helps control your computer is called 1. System software, 2. Application software, 3. Microsoft Excel, or 4. Microsoft Word.
Okay, let's dissect the phrasing of the prompt. Helps control your computer. The test maker is specifically highlighting the management of hardware and low-level resources.
So we can rule out 3 and 4 immediately, right?
Definitely. Options 3 and 4, Excel and Word, are end-user tools. They do not control the computer. They sit securely in user space and have to politely ask the kernel for permission to do things.
Right. And option 2, application software, is just the broad category for those end-user tools.
Yes. But option 1, system software, encompasses the OS, the kernel, the drivers, and the utilities that literally physically manipulate and control the hardware. So the definitive answer is 1.
Perfect. Let's push a bit harder with MCQ2.
1 allows the user to diagnose and troubleshoot the device. 2 is a programming language. 3 is a part of productivity suite. 4 helps the computer manage internal resources.
Now, this is a fantastic question because it features a very strong distractor designed to trick you.
Is it option 1?
Yes. Option 1 mentions diagnosing and troubleshooting. And we just talked extensively about system utilities like antivirus and disk cleanup doing exactly that.
But it's a trap.
It's a huge trap. The question asks for the definition of system software as a whole, macro category, not just the utility subcategory. It's too narrow.
What about option 2?
Option 2 is a categorical error. Software is written using a programming language. It is not the language itself. Option 3 is describing application software.
Which leaves option 4.
Right. Option 4 helps the computer manage internal resources. Perfectly captures the macro-level architecture we just mapped out. Managing memory pages, scheduling CPU interrupts, translating driver signals. These are all internal resource management tasks. So 4 is definitively correct.
Awesome breakdown. All right, we've thoroughly mapped the foundational layer. The OS kernel is securely managing the hardware. It's preemptively scheduling tasks and protecting the virtual memory space.
The building is secure and running.
But a computer that just manages itself is pretty much useless to us. We need it to actually perform work. We need to cross the boundary from kernel space into user space. And this brings us to the second pillar of your exam, application software.
And going back to the textbook definition, application software is defined as the end-user programs designed to help the user perform single or multiple specific tasks.
These are the specialists you hire for the office building. They actually get the business done.
Exactly. They are the tools that justify the existence of the hardware in the first place. But the absolute golden rule you must remember for the exam is the dependency architecture we talked about.
Right. Application software is entirely parasitic.
That's actually a really good word for it.
Yeah.
Parasitic.
Yeah.
It cannot run on bare metal.
A word processor does not inherently know how to send an electrical impulse to an LCD monitor to draw a black pixel on the screen.
No, it relies 100% on the system software APIs, the application programming interfaces to function. Without the OS underneath it, application software is useless code.
Got it. Now, the syllabus splits these applications into 2 distinct architectural camps, general purpose and specific purpose. Let's start with general purpose.
I like to call these the Swiss Army knives of software.
Because they provide a massive open-ended canvas for the user to create almost anything, right?
Exactly. And the first one on the list is word processors. The exam expects you to know what they do and be able to recognize their industry examples.
So a word processor creates, edits, stores, and prints text documents, and it uses a WY's ISIYG interface, right? What you see is what you get.
Yes. It abstracts all the complex underlying typesetting into a visual, user-friendly interface. And the industry examples you need to memorize are Microsoft Word, WordPerfect, AppleWorks, and OpenOffice Writer.
Okay, next up, we have electronic spreadsheets. And here is where test makers really love to drill down into specific, minute terminology. Because a spreadsheet doesn't just hold text, it structures data mathematically.
Yes, the architecture of a spreadsheet is fundamentally different from a word processor. It is built on a strict grid system.
And the intersection of a horizontal row and a vertical column is called a cell, correct?
Right, a cell. But the real power for the user is in the relationships between these cells. When you input a formula, you are essentially building a directed acyclic graph.
A what?
A computational tree. It means that changing one single number in one cell cascades through the entire sheet, recalculating everything instantly based on the formulas.
Oh, got it. And the text elements that describe what those numbers actually mean, like headers, are called labels.
Yes. So for the exam, you need to know those 3 terms: cell, formula, and label. And the industry examples provided for spreadsheets are Microsoft Excel, Coro Quattro Pro, and Lotus 123.
Awesome. Following that, we move from the spreadsheet to the database management system, or the DBMS.
This is a really critical distinction to make for the test. Students constantly confuse spreadsheets with databases because visually they both hold tables of data.
But architecturally, under the hood, they are worlds apart, right?
Completely different universes.
Yeah.
A spreadsheet is designed to hold all its active data in the computer's RAM. So if you try to load 10 million rows of data into Excel, the spreadsheet will choke and crash your system memory.
But a DBMS doesn't do that.
No. A DBMS is designed to sit securely on top of massive storage drives and efficiently query millions of records without loading them all into the fragile memory space at once.
Oh, that makes sense.
It enforces strict relational rules and what we call ACID properties: atomicity, consistency, isolation, durability.
Basically ensuring that the data is never, ever corrupted.
Right. Even if thousands of different users are accessing and changing records simultaneously, it allows you to sort, query, and maintain massive data sets using languages like SQL.
So a spreadsheet is basically an advanced calculator, but a DBMS is an industrial-scale filing system.
That is the exact distinction you need. The industry examples for DBMS in your texts are Microsoft Access, Oracle, and MySQL.
Perfect. The last two general-purpose tools on the list are presentation software and desktop publishing, or DTP. Presentation software, like Microsoft PowerPoint, is fairly obvious. It's designed to synthesize information into visual slides for a projector. But DTP is a bit more specialized.
It is.
How does desktop publishing differ from just a standard word processor? Because, I mean, if I want to make a flyer for a bake sale, I could just do it in Microsoft Word.
You certainly can, but a word processor is designed sequentially. As you type, the text naturally flows down the page line by line.
Right.
DTP software, and the examples here are Adobe PageMaker, Quark Express, or CorelDRAW, treats the page as a rigid blank canvas.
So it's not sequential.
No. Text boxes, vector graphics, and high-resolution images can be locked into absolute exact coordinates on the page. It uses complex commercial color spaces like CMYK, and it have layout algorithms designed specifically to interface with massive commercial printing presses.
So it's really about structural, graphic layout, not just natural text flow.
Exactly. It's for magazines, not essays.
Okay, so that covers the general purpose side of the house. Now let's look at specific purpose software.
These are the highly focused specialists.
Right. These are monolithic programs built to execute one highly constrained set of workflows and absolutely nothing else. Your texts list inventory management systems, payroll management systems, and hotel management systems.
And you really need to be familiar with the niche industry examples they provide for these.
Let's run through them.
For inventory, which is tracking physical stock and complex supply chains, they cite a program called Fishbowl. For payroll managing tax brackets, employee direct deposits, and legal compliance, they cite UltiPro. And for hotel management coordinating room bookings, point-of-sale systems, and housekeeping schedules, they cite Jubo.
Okay, I want to challenge this categorization for a second, because this is where the academic theory hits the messy, real world, and this is exactly what the exam will test.
Let's hear it.
Let's say I go buy TurboTax to do my personal income taxes. Millions of people buy it off a retail shelf at Best Buy every year. Is that general purpose because it's massive mass market software, or is it specific purpose?
It is definitively specific purpose.
Even though everyone uses it?
Yes, because you are conflating the distribution model, mass market retail, with the actual software architecture. TurboTax provides a highly rigid, Rails-based workflow. You answer a specific question, it moves to the next predefined screen, it calculates a specific IRS tax form. You cannot use TurboTax to design a flyer. You cannot use it to track a hotel's inventory.
Its entire code base is dedicated to executing a single specific purpose, calculating taxes.
Exactly. Therefore, it is specific purpose application software.
And just to reiterate our golden rule, regardless of whether it's a massive Oracle SQL database or a specific little tax program, they all still rely entirely on the OS, right? If TurboTax wants to print my return, it doesn't talk directly to my HP printer.
Never. It generates a generic print request, executes a system call, drops down into kernel space, and literally begs the operating system to pass that request to the specific device driver. The dependency is absolute.
All right, let's see how it's manifests in the actual exam. Here is MCQ number 3. The software that is used to create text-based documents are referred to as 1. DBMS, 2. Suites, 3. Spreadsheets, 4. Presentation software, 5. Word processors.
Okay, this is a relatively straightforward definitional check, but let's eliminate the options logically just to practice the methodology.
Good idea.
Option 1, DBMS, is for relational data storage and queries. That's out. Option 2, suites, is actually a really tricky distractor.
Because of Microsoft Office.
Exactly. A suite is a bundle of applications like Office, which contains Word, Excel, and PowerPoint. But the suite itself isn't the specific tool doing the text creation. It's just the packaging.
Got it. Option 3, spreadsheets. We know they manipulate numerical formulas. Option 4, presentation software, creates visual slides.
Which leaves option 5, word processors, which are architecturally designed from the ground up for text-based document creation.
Nice and easy. Let's step it up a notch. MCQ 4. Software designed for a specific purpose or application, such as pay calculations, processing of examination results, etc., are known as 1. Utility software, 2. System software, 3. Application software, 4. Customized software.
Now, this question is a psychological trap. I guarantee it catches students off guard.
Why?
Because the prompt literally contains the exact phrase, specific purpose, so the panicked test taker will scan the answers desperately looking for the term specific purpose software.
But it isn't there in the options.
Right, so you have to zoom out and look at the macro categories.
Okay, let's break them down.
Option 1, utility software, does low-level system maintenance like disk defragmentation. Option 2, system software, manages the hardware and memory pages.
What about option 4, customized software?
It's a highly tempting distractor. While software can certainly be custom-built for a specific company, customized is not the broad academic category your textbook uses to classify end-user tools. The prompt describes things like pay calculations, a task performed in user space to achieve a real-world result for a human. Therefore, it falls squarely under the massive umbrella of option 3, application software.
Because specific purpose software is just a subcategory of application software.
Exactly.
That is incredibly helpful advice. Learner, don't fall for the exact phrasing. Analyze the architectural level of the software they're describing.
Always look at the architecture.
Okay, so we have covered the massive operating systems and the complex applications running on our laptops and servers. But now we are going to leave desktop entirely.
This is a fun pivot.
We are going to look at the computers that actually govern our physical reality, the ones hidden in plain sight all around us. This brings us to the third pillar, embedded software.
This represents a massive shift in how we think about computing. When you interact with application software, on a desktop, you are acutely aware that you are using a computer. You are looking at a screen. You're clicking a mouse.
Yeah, it's a very conscious interaction.
But an embedded system is fundamentally different. It is a microcomputer complete with its own CPU, memory, and software that is permanently physically integrated into a larger, non-computing mechanical or electrical system.
So we are talking about the tiny computers inside microwave ovens, or the anti-lock braking systems in our cars, or digital thermostats on the wall.
Yes, and because they are physically embedded inside machines, they operate under brutal, unforgiving physical constraints.
Because a general-purpose desktop has, gigabytes of RAM and massive cooling fans?
Right, but an embedded system might literally be the size of a postage stamp. It might be running off a tiny watch battery with only a few bare kilobytes of memory.
Which means you absolutely cannot run a massive, bloated operating system like Windows 11 on a heart pacemaker.
No, that would be a disaster. You have to strip away the graphical user interface, you strip away the massive file systems, and you use highly specialized, stripped-down embedded operating systems.
And these are designed to do one single thing flawlessly, right?
One thing, over and over, without fail. And the most critical concept your exam will test regarding embedded software is the RTOS.
RTOS, real-time operating system. Let's dig really deep into the mechanics of this, because I feel like the word real-time is thrown around so casually in tech marketing, but here, in this context, it has a strict, unforgiving definition.
It does. In general-purpose computing, if you click to open a massive Excel spreadsheet, the OS might take, say, 3 seconds to allocate the virtual memory and load the program.
Right. You experience a slight delay, you see a loading wheel, but the system hasn't failed.
Exactly. It's prioritizing fairness among all the 50 processes running. But an RTOS prioritizes determinism.
Determinism, meaning a guaranteed mathematical boundary on the response time.
Exactly. In an RTOS, when a physical input occurs, the software must process that input and generate the correct output within a strict predefined time interval. And we usually measure it in milliseconds or even microseconds.
Wow. And your syllabus divides this RTOS concept into 2 vital subcategories that you need to memorize, hard RTOS and soft RTOS.
Yes, and the distinction is crucial. Let's start with the unforgiving one. hard RTOS.
Okay, RTOS.
In a hard real-time operating system, missing a deadline by even a single microsecond is considered a total catastrophic system failure.
A microsecond.
Yes. The system must guarantee that a task will execute exactly when it's supposed to every single time, without exception.
Okay, let's use a mechanical analogy to ground this. A hard RTOS is not like a hired specialist doing paperwork. It is a vital human reflex.
That's a great analogy.
Let's take the airbag deployment system in a car. The physical sensor detects a massive deceleration. That is the input, right? And the embedded software calculates the crash vector and triggers the explosive charge to actually deploy the airbag. Now, if the software decides to pause for just half a second to run a quick memory cleanup utility.
The driver's dead.
Right.
The deadline was missed, and the output the airbag deploying late is now completely useless, or even more dangerous. The system failed catastrophically.
That really paints a picture.
Things like automatic aircraft landing systems, industrial robotics on an assembly line, pacemakers, these all rely exclusively on hard RTOS.
And how does the software guarantee that speed?
The software architecture utilizes absolute priority scheduling. If a critical hardware interrupt comes in like crash detected, the OS violently halts whatever background task it was doing, drops everything immediately, and executes the critical code instantly.
That is intense. So contrast that with a soft RTOS, because it honestly sounds like an oxymoron. If it's real-time, how could it be soft?
It's a matter of consequences. In a soft RTOS, the system is certainly designed to meet strict timing deadlines.
Yeah.
But if it occasionally misses a deadline, the system doesn't experience a total life-threatening failure.
So what happens?
The performance just degrades slightly, or maybe a specific data packet is dropped, but the machine keeps running safely overall.
What's a good real-world example of that for the exam?
Digital video streaming receivers or modern ATM machines.
Okay, an ATM.
If you request cash from an ATM, the embedded system is processing complex encryption and network requests in real time. But if there is severe network congestion and it takes 4 seconds to process your withdrawal instead of the specified 2 seconds,
The ATM doesn't explode.
right, the transaction just completes late. The technical deadline was missed, you were mildly inconvenienced as a user, but the overall system integrity remains perfectly intact.
Or like a digital TV tuner. If it drops a single frame of video because the CPU is overloaded for a millisecond, the screen glitches for a tiny fraction of a second, but the broadcast keeps playing, that's a soft RTOS.
Exactly. And your text lists a variety of specific industry examples where embedded systems live, which you should memorize. Windows embedded platforms, ATMs, digital TVs, GPS navigation systems, ultrasound machines in hospitals, elevators, and automatic aircraft landing systems.
Let's lock this concept in with MCQ number 5. Where are you likely to find an embedded operating system? 1, on a desktop operating system, 2, on a networked PC, 3, on a network server, 4, on a PDA, 5, on a mainframe.
Okay, this requires us to categorize the hardware platforms based entirely on their constraints.
Right, look for the constraints.
An embedded OS lives on a highly constrained, specialized device. Option 1, a desktop, is a general-purpose powerhouse. Option 2, a networked PC, is exactly the same. Option 3, a network server, is a massive machine designed to handle millions of generalized requests.
And option 5, a mainframe.
A mainframe is the largest, most complex general-purpose computing environment in existence. It handles the bulk processing for entire multinational corporations.
Which leaves option 4, the PDA.
Right. And just for context, since it's an older term, a PDA, or Personal Digital Assistant, is a legacy handheld device from the late 90s and early 2000s, like an old Palm Pilot.
Before smartphones.
Exactly. While smartphones today run massive, complex operating systems like iOS or Android, a classic PDA had incredibly constrained memory, no hard drive, and ran a highly specialized embedded operating system designed purely to manage a calendar, contacts, and simple text notes.
So out of the options provided, it is the only device that necessitates an embedded OS architecture due to its hardware limits.
Correct.
Let's look at MCQ 6, which tackles the definition directly. What is an embedded system? 1, a program that comes wrapped in a box. 2, a program that is a permanent part of a computer. 3, a computer that is part of a larger computer.
Let's analyze the phrasing here carefully.
Option
1, wrapped in a box, describes an old retail distribution method for proprietary application software, like going to a store and buying a physical copy of a PC video game.
Option 2 is tricky, though. A program that is a permanent part of a computer.
It is a very tempting distractor. It perfectly describes firmware or ROM read-only memory, but it only describes the program itself. The question specifically asks what an embedded system is.
Ah, it's asking for the whole package, the hardware and software combined.
Exactly. Option 3, a computer that is part of a larger computer, is phrased a bit awkwardly, but it captures the physical reality perfectly.
Because an embedded system is a complete microcomputer.
Yes, it has a CPU, RAM, and an OS, and it is physically built into a larger mechanical machine like the engine control unit inside an automobile. It is literally a computer inside another machine. So 3 is the right answer.
Spot on. All right, we have covered the managers, which is system software. We've covered the specialists, which is application software. And we've covered the hidden reflexes, which is embedded software.
We're making great time.
Now we must transition to the final 2 pillars of your syllabus. We are moving away from what the software does mechanically, and we're looking at who actually controls it legally. We need to talk about the access divide, proprietary software versus open source software.
This is a fundamental philosophical, economic, and legal divide that dictates exactly how software is engineered, how it's distributed, and how it's audited.
Okay, to understand it, we need to look briefly at how software is actually created in the first place, right?
Yes. When a human programmer writes software, they write it in what we call source code. These are languages like C++, Python, or Java. It is human-readable logic. It looks like complex English and math.
But the physical CPU cannot read C++.
No, it can't. The CPU only reads binary, pure zeros and ones.
Right. So that human-readable source code has to be translated. It's passed through a special program called a compiler, which permanently translates it into the raw binary machine code.
And that compiling process is exactly where the concept of proprietary software comes in.
Okay, explain how.
Proprietary software, which is also known as closed-source software, is defined by the fact that the corporate creator compiles the code into binary and gives or sells you only the binary file.
So they hide the original text.
The original human-readable source code is fiercely guarded. It is literally locked in a corporate vault.
Which means if I buy a proprietary video game, I can play the game, I can run the binary EXFI file, but if I want to look under the hood to see how the graphics rendering engine actually works, or if I want to fix a bug myself, I just can't. It's a completely closed black box.
Yes. You do not own the software. You are merely purchasing a highly restrictive license to use it. The vendor retains all copyright and total control over the architecture.
Now, the syllabus breaks proprietary software down into a few distinct distribution models that you need to be able to identify for the test.
Let's run through them.
First is retail software. This is the classic model. A commercial product sold on a physical store shelf or a digital storefront. You pay $60, you get the binary. Simple.
Yep. Next is OEM software.
OEM stands for original equipment manufacturer, right?
Right. This is a bulk licensing model. For example, Microsoft sells millions of OEM licenses of Windows directly to Dell or HP at a massive discount.
So when you buy the Dell laptop, the proprietary software is already bundled onto the hard drive.
Exactly.
Then we get to 2 terms that always confuse people on exams: shareware and freeware. Let's establish why these are still classified under the proprietary umbrella, even though the word free is involved.
This is a massive trap on exams, so listen closely. Shareware is basically just a marketing model. You download the software for free, and you can use it for a trial period, say 30 days.
Or maybe you can use a crippled version of it indefinitely, with half the features locked.
Exactly. But eventually, you are legally required to purchase a license to unlock it fully. Crucially, during that entire process, you never, ever get access to the source code. It remains a black box.
Okay, but what about freeware? Because freeware is a fully functional program that you can download and use forever, completely free of charge. How is that different from open source?
It is the most critical distinction in this entire section. It comes down to an old adage in the tech community. It's the difference between free as in free beer and free as in free speech.
Free beer versus free speech. Let's unpack that.
Freeware costs $0. You get the free beer. You can use the program forever without paying a cent. But the author still retains the absolute copyright, and they do not release the source code.
So if I find a massive security vulnerability in the freeware, I can't fix it myself.
No. You have to hope the original author eventually decides to patch it. You are entirely dependent on their black box.
And that brings us to the inverse model, our final category, open source software, or OSS.
Open source software is defined entirely by access. In the open source model, the creator writes the program and then publishes the complete human-readable source code to the entire world, often under legal licenses like the GNU General Public License.
So it's free speech. Anyone can see exactly how the code works.
Anyone with a technical skill can download the source code, study every single line of logic, audit it for security flaws, alter it, add new features, and distribute their modified version back to the community.
But how does that actually work in practice? Because if anyone and everyone can just change the code, doesn't it just become chaotic spaghetti code? Like, how does a project survive that?
It survives because it utilizes a highly structured, collaborative architecture, often facilitated by version control systems like Git.
Okay.
If you want to fix a bug in an open source project, you don't just change the main file. You create a branch, a personal copy of the code. You make your fix there, and then you submit what's called a pull request.
Ah, so you ask for permission to merge it.
Exactly. The core maintainers of the original project review your code.
Well,
If your code is good, secure, and actually fixes the problem, it gets merged into the master project. It is a massive, global, peer-reviewed ecosystem.
it's literally the scientific method applied to software engineering. A proprietary black box requires you to blindly trust a corporation. Open source allows thousands of independent engineers to mathematically verify the code.
That's beautifully said.
Oh.
And let's look at the industry titans the exam expects you to know for these two models.
For proprietary software, Microsoft Office is the textbook definition of closed-source commercial software. The Windows operating system itself is proprietary. The .doc file format used by early versions of Word was actually a proprietary secret structure that only Microsoft fully understood.
And for open source?
The crown jewel of open source is Linux.
Yes. In 1991, a university student named Linus Torvalds wanted to build a free Unix-like operating system kernel. He wrote the core code, and crucially, he released the source code to the internet, asking for help to improve it.
And because it was completely open, thousands of programmers jumped in to help, right?
Exactly. Today, the Linux kernel, which has been built collaboratively over 3 decades, runs the vast majority of the internet's web servers, it runs all Android smartphones, and it runs literally all of the top 500 supercomputers in the world.
That's unbelievable.
It is a testament to the power of the open source model. Another key example from your text that you should memorize is MySQL, which is an immensely popular open source database management system.
All right, let's test your ability to navigate this access divide on the exam. MCQ number 7. Linux is a type of software. 1, shareware, 2, commercial, 3, proprietary, 4, open source, 5, hidden type.
Based on our deep dive, this should be a reflex question. Option 1, shareware, implies a trial period. Linux has no trial, it is eternally free. Option 2 and 3, commercial and proprietary, imply a locked, corporate-controlled code base.
And Linux is the complete antithesis of that.
Right. Option 5, hidden type, is just a nonsensical distractor term they made up. Linux was built explicitly by publishing the blueprints to the world. It is the defining example of open source software.
Spot on. Let's tackle the final question for today, MCQ 8. Microsoft Office is an example of it. 1, closed source software, 2, open source software, 3, horizontal market software, 4, vertical market software, 5, compiler.
Okay, let's work through the logic systematically. Microsoft is a publicly traded corporation whose primary business model for decades was selling restrictive licenses to use their software.
They protect their intellectual property fiercely.
They absolutely do not publish the source code for Excel or Word. That immediately eliminates option 2, open source.
What about options 3 and 4, horizontal and vertical markets?
Those terms describe business marketing strategies, whether a product is sold across many different industries, which is horizontal, or designed for one specific niche industry, which is vertical.
So it's irrelevant to the code.
Right. While you could argue Microsoft Office is a horizontal product, those terms do not describe the fundamental nature of the software's code availability, which is clearly the core dichotomy the test is probing here.
And option 5, a compiler.
A compiler is the developer tool we discussed earlier that translates source code into binary. Microsoft Office doesn't translate code. It allows users to write business documents and make spreadsheets. It is an end-user application suite.
Which leaves only one logical choice.
Exactly. Therefore, the most accurate foundational description is that its source code is hidden and locked. It is 1, closed source software.
Boom! This is how you don't just pass an exam, you completely dominate it. You aren't just memorizing dry definitions, you are understanding the actual architectural differences between an OS kernel, a preemptive scheduler, a virtual memory page, a user space application, an embedded real-time reflex, and the legal frameworks of compiled source code.
And having that mental map is exactly what allows you to dissect tricky questions and confidently eliminate those plausible distractors.
Let's do a final rapid-fire structural recap of the 5 pillars to lock it all in.
Sounds good.
Pillar 1, System software, the lowest level, highly privileged foundation. The OS acts as the aggressive bouncer and traffic cop. It preemptively schedules CPU time via hardware interrupts. It manages virtual memory pages to prevent segmentation faults. It maps the hard drive with file systems like NTFS. And it uses device drivers as translation matrices to speak to peripherals. And it uses utilities to optimize and protect that whole environment.
Pillar 2, application software. These are the tools operating in restricted user space, entirely dependent on the OS via system calls. They range from general-purpose canvases like word processors and relational DBMS to highly constrained specific-purpose programs like payroll and inventory systems.
Pillar 3, embedded software. Stripping away the general-purpose overhead to put microcomputers permanently inside other machines. Operating under massive physical constraints, they often rely on real-time operating systems. A hard RTOS guarantees execution to the microsecond for critical safety systems like airbags, while a soft RTOS manages timing for things like ATMs.
And finally, pillars 4 and 5, the access divide. Proprietary software locks the human-readable source code away in a vault, forcing you to rely on a black box binary file, whether you pay for it via retail or download it for free as freeware. Open source software, on the other hand, publishes the source code globally, allowing a community of engineers to audit, modify, and improve the architecture collaboratively, much like the Linux kernel.
If you can visualize that layered architecture in your head, you are going to walk into that exam room and effortlessly deconstruct every single question they throw at you.
You really will.
But, before we sign off, I want to pull back from the exam syllabus for just a moment. We've spent this entire deep dive dissecting the mechanics of software so you can pass a test. But these concepts have profound and honestly sometimes terrifying implications for the physical world you inhabit.
They really do. And this is the thought experiment I want you, the listener, to carry with you. We discussed how embedded software runs our anti-lock brakes, our pacemakers, and our power grids.
Right.
We also discussed how proprietary software is a black box, a locked binary, where the source code is a heavily guarded corporate secret.
You cannot see the logic inside.
So if you combine those two pillars, you realize a startling truth about our modern infrastructure. The vast majority of the critical life-or-death embedded systems that actually govern our physical safety are running on closed-source proprietary code.
Wow. We are essentially living in a physical world governed by black boxes.
Exactly. When a proprietary algorithm fails in an autonomous vehicle, or a glitch in a proprietary fly-by-wire system causes a commercial airliner to pitch downward, the public, and often even independent government safety regulators, cannot immediately look at the source code to see what went wrong.
We have to just sit there and wait for the corporation that owns the license to tell us what happened.
It raises a massive lingering question regarding accountability in architecture. How much of our physical safety, our privacy, and our daily lives are we blindly handing over to digital blueprints that we are legally forbidden from auditing?
That is a heavy, essential thought to chew on. Software is no longer just sitting on our desks. It is the invisible physics of our modern reality.
It really is.
Learner, you have the architectural framework now. You understand the mechanics. We wish you the absolute best of luck on your upcoming university exam. Go crush it, and never stop questioning the underlying logic of the technology that surrounds us.
Good luck, everyone.
Oh, wait.
Till next time.